Hello there, calculus class. It is time to learn about the last section of chapter 3, which is improper integrals. Now, in order to talk a little bit more coherently about what we're doing with improper integrals, we might need to remind ourselves about what's going on with definite integrals, because improper integrals are going to be a type of definite integrals. Remember, the definite integrals are the ones in which we are finding the area under the curve. Another way to say it is between the curve and the x-axis, between some starting point A along the x-axis and some ending point B farther down the x-axis. So in this case, it would be the area of this trapezoid-shaped structure that you're seeing here. But what if one of the limits were infinity? So like if I was trying to integrate some function between some starting point and all the way down the x-axis. Now this is actually a fairly common thing in real world problems. Often you are integrating, for example, maybe the total amount of signal received from some antenna starting at some wavelength and going up to infinite wavelengths, all the wavelengths longer than this size. That's a very common kind of problem. All right, just as an example here, we're going to be talking about when one limit is infinity. For example, here's a problem where I am showing the curve 1 over x, and I'm just trying to illustrate there, shaded in gray, the area between A, where A is 1, and B, where it goes out to infinity. Now, I can't actually do infinity on Desmos, but I put a big enough number in there that you can see there's this little skinny area. And that little skinny area might actually add up to a number. Maybe not, maybe. Whereas some of them definitely are going to blow up. I mean, here is a function that just keeps getting bigger and bigger the farther I go down the x-axis. Clearly, this is not going to settle down onto just a single answer. The farther I go down the x-axis, the bigger and bigger this area gets. I think we need better words than blows up for what we're doing here, though. Because even some of the ones that look okay, like this one, might actually blow up. Just because that area is getting skinnier and skinnier the farther out you go along the x-axis doesn't necessarily mean everything's okay and it's going to come to some particular value, that you'll have some digits that you can use. All right, so if we want a better term than blow up, let's use the words converge and diverge. Some improper integrals converge to a solution. There is an answer that is digits. Whereas other ones do not converge to an answer, they diverge. The farther out you go down the x-axis, the worse the situation gets. So it seems like we're going to have two kinds of problems here then. Ones that converge and ones that, and if they converge, we'll have an answer that's digits, and ones that diverge. So like one like that clearly diverges. The farther out we go on the x-axis, the worse this answer is going to get. But many of the ones that kind of taper off towards the x-axis and get skinnier and skinnier the farther out you go will converge. Now, this particular one that I have up on the board here, though, does not. This particular one does not converge. This particular curve is certainly approaching 0, but in this particular case, it's actually not approaching it fast enough. And so the area under the curve between A is 1 and B is infinity will actually also be infinite. And we're going to see this one. We're going to actually work this one out in a few minutes. But not all of the integrals that look good, that taper off towards skinnier and skinnier, and therefore should be adding up to a smaller and smaller sum, not all of them work. That's where we come to this idea of improper integrals. Mathematicians sure use that word improper a lot. These are improper integrals in the sense that one limit or the other limit is either infinity or negative infinity. All right, I just screen captured here a section from your online textbook here. There's going to be 3 different definitions as to how we're going to deal with improper integrals. And the first one is going to be integrals that start someplace A along the x-axis, but then go out to the infinity on the right side. And we're going to have this really nice definition here. We can substitute that integral for just the integral to the letter t from a to t, And then we will do this as a limit. Here, let's think about this for a moment like this. If that limit weren't there, this whole thing would seem a little less scary. But we would just have the integral from starting place A to an ending place t. And now, well, we're just going to be going, t is going to head on out to infinity. We'll have farther and farther places down the x-axis as we head out towards infinity. All right, let's actually use that. We're going to keep that rule parked over here today. And we're going to start with a problem that actually comes from the pool that your loft assignment is going to be using today. Here we have the improper integral from 11 to infinity of this relatively nasty looking little expression dx. Okay, I always think it's a good idea to graph the function first, and let's just make sure we know what we're expecting here. All right, just taking a look at this guy, I can see on the screen capture here that from starting at 11 and headed off to infinity, this is just some really narrow little piece of area under the x-axis. It's going to be a negative area because it's under the x-axis, and it's a very small little thing. I'm feeling like this one probably converges just by looking at it, but I can tell you that it can be tricky to figure out if it does until we actually work through this definition here. So here's the problem we're trying to solve, and we're going to be making good use of this formula over here. All right, so here's the equation that we're working on. And the first thing I see, of course, is we can always take, in this case, the negative 24 is just multiplied by everything else in the function. We can always just pull that out in front and make this negative 24 times a more pleasant looking integral. Okay, and from our rule that we have over here, we can change that integral into a limit of a simpler looking integral. See, there's no infinity now. The stopping point is t. Okay, so we got this little integral now. We can think about that integral on the inside and worry about that limit later. That integral on the inside is actually just a method of substitution integral. If I just choose u is equal to that piece that was on the inside here, we could do a little method of substitution and eventually get that 1/6 du equals dx. We've only done that about 1,000,000 times already this semester, not to mention towards the end of the first semester. So we have this integral that includes a limit. That sounds horrible, but we're just going to work on the part on the inside right now, the integral itself. And we'll do the method of substitution on that integral. Now remember, we started off, it was an improper integral. It had a starting point at x equals 11 and an ending point at t. Now we've done a method of substitution. And remember, we're not going to bother figuring out the starting and ending points after we've done method of substitution because they always go away anyway. So even though your textbook takes the time to put numbers here where I have these little shaded boxes, these little dotted boxes here, we always call that, it's the integral from who knows to who cares of 1/6 1 over u squared du. We just haven't done one like that in a couple days. All right, because I'm just going to leave those boxes there because in the end they go away anyway. All right, so let's see. We've got this 1/6 in here. We can pull that on the outside and have this ugly thing of the integral from who knows to who cares of 1 over u squared du. And that 24 over 6, that simplifies to just 4. All right, now I'm going to put this up in this 1 over u squared. I'm going to bring it up into the numerator. So that I have the integral, I have a limit of, but I'm not going to think about that limit right now, of the integral from who knows to who cares of u to the negative 2 power. Okay, that's a polynomial. That's our favorite way to do an integral. We can do that guy. We're going to goose the power up by 1 and make it negative 1. You divide by the new power. And then remember, we're going to have this fundamental theorem of calculus thing going on here where we're going to be evaluating it at the ending and starting points of the span along the x-axis that we're integrating over. I want to get rid of that negative 1. We're just multiplying by a negative 1 there. Let's just pull it out. We can always pull that out of a limit. We can always, if it's just a constant times a function, you can always pull the constant out of the limit. Let's just pull that out of there. That negative 4 and the negative 1 becomes 4. And then we've got the limit as t approaches 0 I'm sorry, t approaches infinity of u to the negative 1. I think it's time to go back to our substitution here and remember that u is equal to 6x plus 4. Let's put that back in. So this is now the limit. Instead of being u to the negative 1, it's 6x plus 4 to the negative 1. And now our who knows and who cares goes back to being our original 11 and t. Perfect. So our original problem, well, actually, this was the original problem, but in the first step we got to over here, is now 4 times the limit of this little business that's really a way of saying the fundamental theorem of calculus. Let's actually bother expanding this thing on the inside here. So we got 4 times, remember how the fundamental theorem of calculus works. We plug in the ending point minus, and then we plug in the starting point. Say our ending point was t, and our starting point was 11, so we plugged in the ending point and the starting point there. All right. Anytime you've got the limit of a difference, one of our limit laws that we learned literally back in like September was that's the same thing as the limit of the first term minus the limit of the second term. If you got just two terms hooked together with a plus or a minus, it's the limit of the first term plus or minus or whatever one you have there, the limit of the second term. Okay, this guy over here, we can get less stressed about. This is a limit, but it's a limit of a constant. There's no variables over here. That denominator is going to be 6 times 11 plus 4. That's 70. So it's 1 over 70. The limit of 1 over 70 is just 1 over 70. So that guy got a lot better. And in fact, okay, we've got 4 times this weird limit minus 1 over... Let's distribute the 4 through there. So we get 4 times this limit we still got to deal with minus 4 over 70. That's not such a bad thing. We still got to do this horrible thing here. Except, wait a minute, is that really so horrible? I mean, as t gets closer and closer to infinity, this whole denominator is getting enormous. 6 times a very large number plus 4. This is going to become very, very large. 1 divided by a very, very large number. In the limit, that becomes 0. 1 divided by a big number gets to be 0. So this whole limit right here becomes 0. 4 times 0 minus 4/70ths is just minus 4/70ths. And in this case, then, our integral converged. It came to a particular set of digits. We could put negative 4/70ths into our calculators and actually have digits. We came to an answer. This didn't blow up to infinity or something weird like one of those indeterminate cases like 0 to the 0th power or something like that. It's a proper, I hate to use the word proper because these are improper integrals. It's a good convergent solution. Let's try another one. And this one I'm going to choose something a little simpler just so I don't take like several screens to get through the whole thing. But this integral is just going to be the integral from 1 to infinity of 1 over x dx. Again, on these guys here, I think a good place to always start is just make yourself a graph. In this case, the graph, it's the area under the curve between x equals 1, which is right there, and infinity, which is way out there someplace. It's a nice little skinny region. I feel like this should converge. I'm going to be wrong. This one's going to turn out to be divergent. But we'll get there. It looks like this should work. This is worth doing the work. All right. Our basic rule that changes this improper integral, because it has an infinity as one of the limits, into an integral, but then the limit of that integral, tells us that the thing here on the left-hand side can become this on the right-hand side. We got the limit as t goes to infinity of 1 to t, the integral from 1 to t of 1 over x dx. Okay. The integral of 1 over x dx is the natural log of absolute value of x. I didn't put the absolute value symbols in there because it got a little bit wacky to have absolute value signs right next to that evaluated at sign. It got a little confusing. And since our points were all positive here, from 1 to positive infinity, we don't need the absolute value anyway. So we got the limit as the natural log of x integrated from, evaluated at t and negative 1. Okay, that's a fundamental theorem of calculus thing. So we're going to plug in the value at the end of the integral, at the ending point, minus, and then the value at the start of the integral. So since we're integrating from 1 to t, then it'll be natural log of t minus natural log of 1. Natural log of 1's, well, actually, I guess technically to do this more accurately, let's first distribute that limit. Okay, the limit of two different functions connected by a minus sign, that's one of our limit laws. The limit of two functions is the limit of the first one minus the limit of the second one. And that second one's not so exciting because the limit of 1, the natural log of 1 is just 0. This is just the limit of a constant. That's pretty straightforward. That's just going to be 0. So I've got the limit as t approaches infinity of natural log of t, and then the minus 0. Well, that doesn't do us any good. But what are we going to do with that limit of the natural log of t? Well, we could make ourselves a graph in Desmos. We could play with our calculators. We could think about it a number of different ways. But here's the deal. There's no end to the natural log. It doesn't approach something asymptotically or anything like that. The farther you get out in the x-axis, the bigger the value of natural log gets. The domain of natural log goes all the way out to positive infinity, and the range it goes up to positive infinity. There is no number. This does not ever calm down. As you go out to infinity, the natural log goes out to infinity. So this whole term here in parentheses becomes infinity. Infinity minus 0 is infinity. Even though that area looked skinny and narrow on our little graph in Desmos a minute ago, it's not skinny and narrow enough. It does not actually converge to a value. The farther out you go on that x-axis, the bigger the area underneath is, and it's not slowing down fast enough to keep from getting to infinity. It is a small thing. It approaches infinity slowly, but it still approaches infinity. We would say that this one diverges. There's not a real number that is the area under that curve. The rule we have been learning so far is this rule 1 that's up here. For when the integral starts at some place on the x-axis and goes to infinity. There's a very similar rule for ones where we go from negative infinity on the left to some stopping point b on the right. So it's the same kind of game, except for now we're on the other tail of the function, headed off towards negative infinity, and it's not terribly surprising that it's basically the same rule. We changed the integral, instead of being the integral from t to infinity, from negative infinity to b, it's now from t to b, and t is going to approach negative infinity. This can be just a nice little way to rewrite an integral when it's an improper integral. So let's put that formula that we just were talking about up here, and let's evaluate this improper integral. It's the integral from negative infinity, so it's an improper integral, and it's this rule 2 type, where it's coming from negative infinity all the way off to the left to 2 of this integrand. Now, on this particular one, I'm going to give you a little bit of scaffolding here, and so do I on the homework. On the homework, whatever you need is in the problem. And in this case, I'm giving you an integral from the table of integrals. For what it's worth, you could have gotten this guy. This is a trig integration example, like from section, 3.3 or something. But that's not what we're doing today. We have enough to do today. We don't need to know. We'll just work with that one as, it comes from a table of integrals or whatever. All right. Again, I always think it's for the best. Let's at least look to see if this one makes any sense. So here's my function, and I'm integrating it from way the heck out there to the left to a stopping point of 2, and I get this area here under the curve. It doesn't look like it's blowing up. I feel like it's converging to an answer. I might be wrong. I feel like it's converging to an answer. Let's see what we actually end up with. Okay, so here is the problem we're trying to solve. And our rule tells us we can change this improper integral into the limit of a much nicer looking integral from t to 2. I mean, that doesn't look wildly different, but this business of having infinity as one of the stopping points of my integral does seem a little bit Scary. All right, so let's see what we can do with this here. Well, let's take that rule that I gave you on the previous slide and say, I know that this integral right here is actually this. It's the inverse tangent of blah, 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 evaluated at the ending point and the starting point of that domain. Okay, well, I hate all this square root of 4s that are in here. Let's go ahead and just take a moment to change them over here to 2s. All right, fundamental theorem of calculus time here. We're going to take this guy and start expanding him. The integral evaluated at an ending point and a starting point. So first we plug in the ending point minus, and then we plug in the starting point. Our ending point was 2, and our starting point was t. Still at the limit of all this. We'll cross that bridge when we come to it. But we have the limit of the starting point minus the ending point. All right, the good news is everything over there on that left term is going to be pretty straightforward. Let's see, I've got the limit of the difference between two functions. That's a thing we know. We know we could take the limit of the first function minus the limit of the second function. That's a rule that we did when we learned limits back literally in like section 2.2 of Calc 1 or something like that. Okay? The limit of the difference between two functions is the limit of the first function minus the limit of the second function. Okay. This guy is not such a horrible thing. See, everything over here is a constant. There's no t's in any of this. It's just going to be the inverse tangent of 1 over 2. Well, the limit of that is just going to be inverse tangent of 1 over 2. Now we got to take some thinking as to what that is, but it's just that was the limit of a constant. The limit of a constant is just the constant itself. So we've got the inverse tangent of 1 over 2. Inverse tangent of 1 is pi over 4 divided by 2. Pi over 4 divided by 2 is pi over 8. So far, so good. But we still have this beast to think about. The limit as t goes to negative infinity of the inverse tangent of t over 2 divided by 2. All right. That divided by 2 is the same thing as multiplied by a half. Well, we are just multiplying inside of a limit. We have 1/2 times some function. We can always pull that to the outside. You can always take if you've multiplied by some constant inside of a limit, you can always pull it to the outside so that 1/2 becomes 1/2 times the limit of just the numerator of that guy. Again, rules that we learned quite a bit back in like September. Question is, what are we going to do with this? All right, I want the limit as t goes out to negative infinity of the inverse tangent of t over 2. There's lots of ways I could think about solving this, but right now I feel like a graph suffices for what we're doing here. Today is not really about limits. Today is not really about inverse tangent functions or inverse trig functions. Let's make a graph of the inverse tangent of 1 over 2. I have to actually use x because Desmos isn't so thrilled about using t most of the time. So here is my function, inverse tangent of x over 2. It's this red line on the graph here. And I can see that as it heads out towards negative infinity on the left, it's getting closer and closer to some asymptote there. And in fact, that asymptote is negative pi over 2. I'm not exactly proving this right now, but that's okay. As we head out to bigger and bigger numbers on the left side, more and more negative numbers, we're getting closer and closer to the value of the arctangent being negative pi over 2. Let's just plug that in. This limit sure looks like it's negative pi over 2. So we just took this limit and called it negative pi over 2. That's not exactly a proof. That's not exactly a great thing to be showing you. But let's just work with that right now. So I've got pi over 8 minus 1/2 times negative pi over 2. That's pi over 8 plus pi over 4. That is 3 pi over 8, which is in fact the right answer. This integral evaluates, it converges to 3 pi over 8. There's a finite area under that curve between negative infinity and 2. And it works out to 3 pi over 8. There is a third version of this rule right here that basically says, what about situations where both the starting point and the ending point of the integral are at infinity? One's at negative infinity and one's at positive infinity. Again, that's actually a fairly common thing in probability, in lots of physical applications. And the trick here is just to break that up into two improper integrals. You can always break an integral up into two pieces as long as the stopping point is between the starting and the ending point. Anytime you have a starting point and an ending point, you can always break it up into two integrals with that new kind of middle point being somewhere in between. It doesn't have to be exactly in the middle, but you can always break it up into two integrals. So here, they recommend breaking up into an improper integral that goes from negative infinity to 0 plus an improper integral that goes from 0 to infinity. And they breaking it up at 0 is actually a good idea because often the integral is just awfully easy to evaluate at 0. Although, as it points out, actually any value would work between positive and negative infinity. It's just that most of the time, your best option is 0. So let's do another improper integral. Here's this guy here. It's the integral from negative infinity to infinity of 2 over 1 plus x squared dx. And I'm going to give you a little hint. Again, this one comes from the day that we did trig integration. It also was on the table that we used during table of integrals. But here's a little thing that'll take a couple steps out of our problems today. All right, we'll keep that in our pocket. And we'll keep this rule handy. And we'll see what we can do here. So here's the integral we're trying to evaluate. And my first thought is always these kind of constants that are just multiplying some function by, it's always best to just get those out of there. So instead, it's 2 times the integral from negative infinity to infinity of 1 over 1 plus x squared dx. Okay. Let's apply this rule right here. We're supposed to take this integral, which goes from negative infinity to infinity, and break it into two parts. A part that is from negative infinity to 0, plus a part that is from 0 to infinity. Got two different pieces there. All right, let's evaluate those two pieces separately. All right, both of them follow rules. Well, this one follows that second rule because it starts at negative infinity. Well, we have a rule for that. It's the limit as t approaches negative infinity of the integral from t to 0 of that function. That was our rule that we learned the second rule. And for what it's worth, over here, this other piece of the integral from 0 to positive infinity will be our first rule, where it was the limit as t goes to positive infinity of the integral of 0 to t of our function. See, we're combining the three rules that we've learned today? Okay. We were told as scaffolding in this problem that this integral, the integral of 1 plus 1 over x squared, is inverse tangent of x. Since it's a definite integral, it's got starting and ending points. It's this, what we gave us, evaluated at the ending point and the starting point. Plus, same thing over here. We had this integral. We were told in the scaffolding for the problem that that is inverse tangent of x. It's going to be because it's a definite integral evaluated at starting at 0 and ending at t, then we're going to evaluating it at t and 0. All right, so we're going to plug those guys in. Now, just because the screen's only so wide, I'm only going to do the left part of it first. We'll come back and get this other piece later. All right, What does this definite integral here mean? It means plug in the ending point, minus plug in the starting point. That's the fundamental theorem of calculus. When you have a integral from a starting point to an ending point, you write it as here's the integral evaluated at the starting and ending point, and then you evaluate it that way. Okay. The inverse tangent of 0 happens to be 0. That got simpler. Okay, but what am I going to do about this guy? Inverse tangent of t as t goes to negative infinity. Today, none of the problems mislead you. If you just get to a point like that and then pull it up on Desmos, what does it... Look, inverse tangent of whatever. I can't do t on Desmos, so we'll do x. All right. Notice as you head off to negative infinity, it seems to be approaching some line, and that line seems to be negative pi over 2. None of the problems I'm giving you today mislead you. Okay, it isn't like it's not, or at some point it's going to cross this line or something. If it looks like it's approaching the line, it is. So, this term right here, this is the limit. Okay, actually, there's a little bit of algebra here. This was 0 minus that, so we had negative inverse tangent of t, and then I pulled the negative sign out in front. I wouldn't have had to do it that way, but that's the way I did it. All right, then looking at the graph, we decided that the limit as t goes to negative infinity of the inverse tangent of t, we decided that that sure looked like negative pi over 2. And again, I'm not misleading you on any of them. Any of them today, if it looks like it's going to that limit, life is short. Let's just do ones that if it looks like it's going to a limit, it is. All right, well, we got a negative of a negative. Let's simplify that. That's just pi over 2. Okay, well, now we got this guy. The limit as t goes to infinity of the inverse tangent of x evaluated at t and 0. Okay, well, this is another fundamental theorem of calculus thing. So we're going to plug in the ending point minus plug in the starting point. So it's the limit of, and here we go, the limit of plugging in the ending point, so we put the t in, minus, and then plugging in the starting point. Inverse tangent is 0. Inverse tangent of 0, once again, is 0, so we get to subtract 0. Yay, that's great. We got the inverse tangent of t. No, we've got the limit as t goes to positive infinity of the inverse tangent of t. For today, it's good enough to say, let's go take a look and see what the inverse tangent of t looks like. So here I pulled up another part of that same graph in Desmos. Here I have graphed the inverse tangent of, okay, I called it x here instead. But as I go out towards positive infinity, it sure looks like it's approaching some asymptotic line. And in fact, it is. It's approaching pi over 2. Okay. That's good enough for today. For today, we're going to say that means as we went out to infinity, the limit was pi over 2. That is fine with me. So we're going to say that this limit is pi over 2. Pi over 2 plus pi over 2 is pi. 2 times pi is 2 pi. And that is our answer. This integral converged. It came to actual digits. That's fantastic. The area under that curve from negative infinity to infinity actually works out to 2 pi, which is crazy. Now, the ugly reality of the whole situation is that there are other ways to make improper integrals. The only ones we've seen so far is with the starting point at any point of the integral, to use the term we use in this class. One of them was infinity or negative infinity. There, in fact, are other ways to do it. Look in the distance. We can just barely see coming up over the trees in the distance something called discontinuous integrands. This is when the, well, like for example, this one right here, it does seem like you should be able to find the integral, the area under the curve of this thing from, I think I labeled it, negative 2 to 2, but it blows up. The function actually blows up, goes to infinity right here. Does that result in something? In this case, by the way, notice it actually decided it was undefined. Desmos thinks it's undefined anyway. Okay, this is a whole nother thing. Any kind of time that the integrand makes a function that has discontinuities, whether they're replaceable discontinuities or jump discontinuities or infinite discontinuities, remember all those terms from back in like October? The truth is there may or may not be, it may or may not converge. The integral may or may not converge. That is a battle to have some other point, a time. And the truth of the matter is these kinds of discontinuous improper integrals never seem to be on Ivy Tech's final anyway for Calculus 2. So for now, I think we have enough to do for today with just the ones that are improper integrals where one of the limits of the integration is either at negative infinity or positive infinity, or they're both at infinity, and that is good enough. So what you're going to have to do is, for next time, there's no exit ticket. What I want you to do is the problem set that I'm posting, which I think only has 2 groups. Okay, please don't guess on these problems. Come to me with any problems that you're having, and I appreciate all your time and attention on this.